Good morning, ladies and gentlemen. Welcome to Physics 30, Electromagnetic Radiation, EMR, Lesson 7, Waves versus Particles. Now, big question pre-1900 for physicists, is light a wave or a particle? Well, there's lots of wave evidence, reflection and refraction. Remember Snell's law? We did that. That's evidence of waves, the derivative. Now, if we look at particles versus waves, firing particles through a barrier with two slits, we will get two lines like this. Line here, a group here and a group here. If we have waves going through the same two slits, we will get an interference pattern. Now, I'm trying to draw this interference pattern here on the board. It's not particularly good. I want you to pause the recording now and go to the video I posted. Now, the video is kind of comic, but the first minute and 45 seconds nicely explain this and show it really nicely. After that, it gets into quantum mechanics. I don't want to talk about that right now. So go watch the video for the first minute and 45 seconds, then come back here. Then you see waves versus particles, okay? Seriously, go watch the video. All right, welcome back. So what I was trying to show is that Young did this double slit experiment, Young, Queen of Diamonds. It's diffraction. He used a light source and he shined through two slits. Now, he got an interference pattern here which shows light as a wave. Now, each of these nodes are bright spots, so antinodes. Antinodes, the bright spot. Destructive interference are the dark on the nodes where they cancel out. Now, we have the central antinode here. Then we have the first antinode on each side. Then we have the second, which is the second one over. And there's the other second. And so on, and third and fourth and fifth. Now, why do we number them? Well, we're physicists. We number everything. Plus, if we're doing measurements, sometimes it's easier to measure to the second or the third because the distance between the center and the first might be very small. Anyway, now, Young came up with a formula for this. Now, it is a little bit difficult, but first things first, I have to draw. Here's some waves. Now, notice that's 1, 2, 3, 4 waves. And if we have the same wavelength of light down here, 1, 2, 3. And yeah, that is a horrible drawing, I agree. But I want you to notice the difference in wavelength is exactly 1. So the waves will constructively interfere. Now, as I said, I can derive the formula, I just don't want to because it's too much work and you don't need to remember it. But the formula here is the wavelength is d sine theta divided by n, where lambda is the wavelength of the light, d is the distance between the slits, theta is the angle of diffraction, and n is the number of nodes. Now, that's the angle of diffraction there. Oh, sorry. The other way to measure the angle of diffraction, if you think about it, that's also the angle there between the slits. Okay, that's easier to measure. So let's do a couple calculations. So what's the angle of diffraction of the first maximum produced by light, wavelength 410 nanometers, through a diffraction grating where the slits are 6.00 times 10 to the minus 6 meters apart? Well, lambda is d sine theta over n. That's a formula. Now I should be drawing a picture here. Come on, stop that. Okay, that's supposed to be go down. So my light waves shoot this way, and I get an interference pattern between the center and the first. That angle theta. Distance is distance d is 6.00 times 10 to the minus 6 meters, and this is the first interference pattern, or the first node, antinode, I'm sorry. So lambda is 410 nanometers 410, sorry, 410 times 10 to the minus 9 of a meter. That's what nano means. D is 6.00 times 10 to the minus 6 of a meter. N is 1, and theta we don't know. That's what we have to find. So I feel like rearranging the equation today because I can. So n lambda equals d sine theta, or sine of theta is n lambda over d 1 times 6.00 times 10 to the minus 6 of a meter. Oh, sorry, that's lambda. Never mind. 410 times 10 to the minus 9 of a meter. Thank you for pointing that out. Should have said it louder so I heard it earlier. Times 10 to the minus 6 of a meter. So sine of theta. Grab your calculators and plug some numbers in. I got 0.06833, and remember, you go to 4 decimal places at least, or in this case, 4 numbers. Theta is sine to the minus 1, and make certain your calculator's in degree mode, guys. And what is that? Inverse sine, I got 3.92 degrees. Okay? So, that's a very small angle. So that's why sometimes we measure n is 2 or n is 3, so we can get better better numbers, or easier to measure. So far, so goodish? How can I confuse you with this? Glad you asked. Now, note if theta is less than or equal to 10 degrees, then sine of theta is really approximately tan of theta, which is x over L, where x is the distance between the antinodes and L is the distance between the slits in the screen. So if I've got my 2 slits like this, L is my distance this way, and x is my distance between the antinodes. And here's where it's sometimes better to go antinode number 2 or 3 or 4, slightly bigger distance, because when you're getting into a fraction of a millimeter, it's hard to measure. Anyway, now I'm going to say this once nicely. On the diploma, and hence on the test I'm going to give you, never use this, ever. Because I will give you a question where theta is greater than 10 degrees, but I'll give you x over L, so you just plug it into this formula, and you get the answer wrong. All right? Now, let me show you. Look right off a diploma. Light falls on a pair of slits 1.28 times 10 to the 5 meters apart. The third antinode are 4.11 times 10 to the minus 2 meters apart, and the screen is 1 meter from the slits. What's the wavelength of the light? Well, your first thought L is 1.00 meters. X, which is 4.11 times 10 to the minus 2. And the screen is, what is the wavelength of the light? Oh, and here, it is here, D is 1.28 times 10 to the minus 5. All right? So, what's the wavelength? So your first thought, lambda equals xd over nl. But, what's the angle here? Let's go back to this nice right angle triangle. What have you got? Well, tan of theta equals opposite or adjacent 4.11 times 10 to the minus 2 of a meter over 1.00 meter. That is 4.11 times 10 to the minus 2. So theta, 10 to the minus 1. So grab your calculator and tell me what you're getting. Sorry. So I got 2.35 degrees, so oops, we can use it here. Never mind. Check your angle, I should say. So lambda is x 4.11 times 10 to the minus 2 of a meter times d 1.28 times 10 to the minus 5 over third antinode, so it's 3 times 1.00 meters. So the wavelength of light here is 7.98. 7.98 times 10 minus 7 of a meter. 798 nanometers times 10 to the minus 9, or 798 nanometers, which puts it, what, in the infrared. Okay, now, so it's going to say, check your angle. This one, yeah, it's too nice. That actually works. We can use this cheating shortcut. So I'm going to change the question to 0.187. Now, I want you guys to calculate this, go back and do this and realize, oh, that's too big. Doesn't work. It's beyond 10 degrees, so you have to use d sine theta over n. All right, so go do that. Now, moving on. How many slits per meter does a diffraction grating have? The second maximum occurs at an angle 16 degrees when the wavelength is 530 nanometers. All right, so how many slits? What's D? Now, so draw the picture. It is 16 degrees. Diffraction of the second maximum, so the n equals 2. So I've given you n, and I've given you wavelength, lambda. So lambda is d sine theta over n. So we're solving here for d. Lambda n equals d sine theta. D equals lambda over n times sine theta. Notice I'm in the mood to rearrange the equations today, because I am. So wavelength is 530 times 10 to the minus 9 of a meter times 2. Sine is 16 degrees. Distance between the lines is 3.846 times 10 minus 6 of a meter. Now, careful here. What's the trick? Well, the question I'm asking is how many slits per meter? Well, this is meters, technically, per slit. And we're asking for what? Slits per meter. That's not called slit. It's got meters per line. That's better. I prefer that. And what we're asking for is lines per meter. Because that's usually what they'll talk about, how many lines per meter. So this becomes 1 over d, which is 1 over 3.846 times 10 to the minus 6 of a meter. So how many lines per meter here? 2.6 times, no, 2.60 times 10 to the 5 lines per meter. Now, I want you to look at that and absorb it, because there's one more little trick. So they talk about slits per meter, or lines. I prefer lines rather than slits, but whatever. Now, careful, they will sometimes do this in centimeters. How many centimeters in a meter? 100. So it's 2.60 times 10 to the 3 lines per centimeter. Okay, so be careful of that. Okay, so far so good. Now, here's a point where I'd ask you to do the diffraction lab. If I can get the camera to work, I'll show it to you. If not, good luck. Anyway, so here's where I normally pause and ask you to do do the diffraction lab. All right, so pause, pretend, go see if I've got the video done for that, then come back later.